Yeah, it's pretty funny. So yeah, my name is Vincent. I'll be giving a talk to you about writing bootkits for embedded devices that are based on U-Boot. I was supposed to do this talk with a colleague of mine, but yeah, he did not decide to show up because I guess he doesn't like spicy food that much. So first I'm going to talk a bit about who we are, why we did this, and then I'm going to talk about the device we used and some preparations we made to the device in order to make this work. Then I will talk about the bootkit itself. I will first start with the actual bootkit, which is based on U-Boot. Then I'll start about how you can use the bootkit to influence the kernel or do cool stuff as persistence. And then I'll end with some recommendations on how to secure these embedded devices and to protect against these sort of attacks. So, as introduced, my name is Vincent. I work for the KPN Red team in Amsterdam. I'm also a new Amsterdam chapter head, all together with Bipin. Yeah, I like Linux, I like low-level stuff, so this is a perfect talk for me, I guess. And I used to work as a consultant, but I decided to sit in an office with a laptop is way better than going to clients all the time. Yeah, my partner who's not here, Bernardo, he also works at the KPN Red team. He's very good at bricking routers. He's even better at bricking routers than I am. He's a Daguni CDF player, and he's a Brazilian who lives in Amsterdam at the moment, and he's actually right there, right now. And a small disclaimer about the talk: we did everything together. So yeah, the entire bootkit was his idea, and we worked together on it, and we came up with this implementation, which is pretty cool. So the goal of the talk was for us to demonstrate that it's possible to have a bootkit on embedded devices, because we know about bootkits in BIOS and UEFI, but I'm not sure if there's any research done on bootkits on routers or other embedded devices. And it's also it's fun to do research like this, and I see Azim go crazy there. And of course, having fun is like one of the main goals, and having a free ticket from my company to India, which is also pretty cool. And yeah, that's it basically. So having a bootkit has several advantages. One of the main advantages is that it's very difficult to detect. The bootkit, the bootloader in this case, is on embedded devices the very first thing that is kicked off. And if you are persistent in the bootloader, then yeah, people usually don't touch the bootloader, so it's very difficult for them to find out that it's compromised. Also, the bootloader is usually not affected by updates. I mean, imagine you updating your ISP's router at your house and it doesn't boot anymore. Yeah, that can happen if you start touching the bootloader and have a small corruption in there. It's also, yeah, you can also bypass OS security features by having a bootkit like this, and you can also bypass the OS altogether by just booting your own kernel. That's pretty cool. The disadvantage is basically what you will see on the slide here. It's if it goes wrong, it really goes wrong. The NSA allegedly tried to backdoor a Syrian router or modem, a backbone router, I believe. And they made a mistake which brought the entire Syrian internet down. And yeah, if this was a bootkit, they might have made a mistake and just rendered the device unusable. So yeah, router malware is hard, and it's very specific to the device you want to backdoor. There are some very specific variables. So yeah, you need to do some research in order to make it work. The device we initially used was the GLINet 6416. It's basically an open source device. It has a 64 megabyte DDR1 RAM, which is on the left side. It has a Atheros 9331 SOC. It has a serial interface, some GPIO ports, and a very cool magnetic-enabled Ethernet adapter, which I don't know what that means. The important part is on the back of the device. You can see there's I didn't put a circle around it, but there's an 8-pin. Let me just point it out on this side. There's like a 8-pin firmware chip in there. In this case, it's a WinBond. As you can see, there are no physical impediments around the firmware. So if you want to refresh it, you can just go ahead and refresh the chip. What we did is we desoldered the actual chip, and where the pins were from the chip, we soldered some wires on. And then we put our device programmer adapter on it. So we put the chip in there, and by connecting all the wires to the correct points, we could basically boot the device like this. And when we would brick the device, we had made a backup with our device programmer, which you can see right here. We could just put our backup back really easy. Instead of like continuously resoldering the chip on it, we can just attach it, make a backup, put the backup back, and then connect it, and it will be working again. And we were very happy that we did this because we had lots of bricks and lots of recoveries. Before I went to India, I actually lost the entire flash chip, so I had to find another device, desolder that chip, and use the backup to put everything back. And before I was doing a talk in Portugal, the day before we were recording demos, I also bricked the device. So yeah, if we didn't do this, then it would be awful stuff. One of the most important parts, requirements actually for doing this is having a good tool chain, because you're going to need to cross-compile different architectures. So basically, what I have an x86 device, the router is a MIPS device, so I need to have a GCC that can cross-compile the code to MIPS, for instance. You can use a great tool for this. It's called CrossToolNG. It's a versatile toolchain generator. You can basically generate toolchains for all sorts of architectures. But what we ended up using, which was way simpler, was using the OpenWRT SDK. Because the OpenWRT SDK for this device, you could just download the entire SDK, which had all the pre-compiled compiler binaries which are made for this architecture, and it saved us a lot of time. So yeah, why did we choose U-Boot? Well, as you can see in the blue square, U-Boot is more than half of all embedded devices run U-Boot. I know for a fact that some Alpha AVAS cards, they have U-Boot, televisions have U-Boot, of course routers have U-Boot, many devices. And U-Boot is open source, so you can just download the source code and you can make some changes to it. There are a lot of open source U-Boot implementations for all sorts of devices. And we ended up using a U-Boot mod from a guy named Pepe2000, which had some modifications that were perfect for a bootkit. And you can also see that the big red share over there, it's CFE, it's a Broadcom, it's a proprietary bootloader, and it also has a big share, but luckily not as big as U-Boot. So if you have a U-Boot image, the first 123K bytes will be like the text tone and the code bases actually, and then at the very end of the U-Boot image, you will have 5K, which are reserved for environment variables. And depending on your device, the environment variables might be located on a different part of the image, but usually the size is about 5K. And environment variables are really useful because they are on persistent storage, and you can set environment variables from U-Boot and they will be safe. So when you reboot the device, you can still have your environment variables. And there are some very interesting environment variables that we will backdoor, and you'll see later that's pretty useful. So a few of these variables are the bootcmd command, for instance. It's the actual first command that U-Boot will kick off when you don't press a key to enter the bootloader menu. You also have bootargs environment variable, which contains the kernel arguments. The arguments are passed to the kernel, so the kernel can set up the device correctly. There's also a load address argument, which is basically the TFTP boot load address. And there's also a recovery environment variable, which contains an entire U-Boot script for recovery. So it can basically make some if statements in there, and it will spawn an HTTP server, and you can use that to recover, it could rescue your image. In this beautiful Radari output, you will see a nil byte separated list at the very end. It's highlighted. You can see like there's the bootargs, and then at the end of the bootargs, you see a nil byte with like the boot delay, and it's basically nil byte separated array of environment variables. Another way of creating a backdoor is by extracting the U-Boot, decompressing the U-Boot, and changing these variables with a hex editor, and then you could put the image back together with LZMA, and you could also upload it on a device. And then if you have the correct CRC32, then you can basically do it like this as well. It's a lot less invasive than flashing an entire bootkit than we do, but it's kind of hard to do this correctly, because to put the image back together, you need to have the correct LZMA algorithm, and it might be specific for different devices, so it might be a pain. Other interesting features in U-Boot are the printenv command. It prints environment variables, the TFTP boot command, which can be used to boot images from the network. TFTP boot can also be used to, you can also use it to load like a U-Boot in memory and then copy it to a different memory section. You can basically write with it as well. And we also have the env stop string feature, which is basically an environment variable that it works as a passphrase to enter the bootloader menu. And also, of course, the bootcmd, which is the command I explained, and the ping command, which is basically an ICMP ping, where you can do some network discovery or see if a server is online or not. In this example right here, we have a dual boot example. So we use the ping command and the scripting language from U-Boot, which kind of looks like Bash. We see with a ping command if the server IP is up, And then if the server IP is up, we TFTP boot to the load address environment variable our backdoor image. And then if it's successful, we basically boot the backdoor image by using the load address environment variable. And if the ping fails, then we basically boot the normal firmware, which is located at the firmware address, which is also a hard-coded environment variable. So yeah, one of the functions we backdoored was the printn function, because yeah, when you manage to get to the bootloader and you want to print environment variables, we don't want you to see our actual backdoored environment variables. So what we did is we added a new function called getMatch to get the name of the environment variable. So we read an environment variable from the list until the equal sign, and then we pass the string to a function that sees like, okay, if this is bootargs, which we basically backdoored, as you can see below in the if statement, if bootargs matches the string from the environment variables, we set the p flag equals 1. I just need to point it out, the p flag equals 1. So if we find a match, which could be bootargs, we set the flag p flag, and then it chooses not to print the environment variable here. So if p flag is not set, we print the environment. So if it is set, it won't print it. And then we will just print the hard-coded environment variables here. In this case, there are 2 environment variables, but so I think they're alphabetically ordered. So you can just basically find out which number is associated with which bootarg, with which environment variable, and then you can use a listing like this to hard code print the environment variable. Sorry. Another function we used was the bootcmd variable. What we did is we override the bootcmd in the source code, because as I explained, the bootcmd is the first command that's executed when the device boots. And what we did here is that we overrode in source the bootcmd command with our dual boot U-boot script. So when a device will first boot, it will just see if our server is alive, and when our server is alive, it will then download our backdoor kernel image, and it will boot that instead. And if our server is not alive, the device will just continue booting. I have a demo where I can show this at a later stage. So yeah, the U-boot environment stop string was an interesting feature. Despite some Google searches that might tell you that this is a security feature, it is not a security feature. If you would set an environment stop string like super secret, if someone managed to dump the flash of your chip, they can run strings on the image and they could just see the password. So this is not a security feature. It's just an inconvenience for people that want to protect they want to protect the bootloader. So it's just an inconvenience for us researchers that we have to dump the flash in order to get get access to the bootloader. What we did, we changed this password feature a bit, and when a guy wants, or a girl, someone wants to access the bootloader and types like any key, it will wipe the entire flash image, so that people that want to do forensics, they can't get to our device because we wipe it. So what it will do usually, it will boot, and then it will prompt you for a key, and if you press a key or a password, you'll get to the bootloader, and if you don't press a key or password, it will just continue booting. So yeah, the moment you press a key, in our case, it will start wiping the flash. What we also did is hiding from strings, because as I said, if you run strings with a normal environment variable, you can just see it. So we made a byte array. What you can see here, you see like the character array is called stop. Well, it's basically a ASCII encoded string which says super secret. And then we use malloc and string copy to put that in the environment stop string variable. So what this ends up doing is that when you are reversing the image over running strings, you won't see anything, but instead you will see, like shown below, you will see individual bytes being moved into a string, and it's harder to reverse it that way. I mean, if you would get to that part, you can obviously see it like getting all the bytes individually, but yeah, running strings and finding it is it's kind of hard. And I'm going to show you how we bypass the environment stop string variable. We will do this by glitching the data in pin. In the demo, you'll see that I will pull 2 blue wires apart. At the moment, we're trying to boot the kernel. So what happens is that when you're booting the device, it first loads the bootloader in memory, and then it tries to boot the kernel. And right when it tries to boot the kernel, we just pull apart 2 wires, and it fails. The U-boot will fail, and it will fall back into the bootloader menu. So yeah, it's for a password protection mechanism. That is, yeah, that's not very good. Just, get the demo there. I brought the device to India with me, but yeah, when I was preparing my talk just a couple minutes ago, I found out it doesn't work. But if you want to have a look at it later, yeah, I can show you and see what it does. Do you see the demo now on the screen? Yeah. So let me explain what happens. Yeah. So yeah, we just pull it, and we have access to the bootloader. So this is also a method that works on devices you get, like a TP-Link, for instance, has a passphrase, an environment stop string. If you just glitch the data out pin when it tries to boot the kernel, you can get into the bootloader and you can just set one of the bootargs to the kernel. In it is bin bash, like you would do on a normal Linux system, and you can get an immediate root shell on the device. So yeah, now we added some features. We're just going to compile the bootkit. So it's very important to add your toolchain to the path, because otherwise you'll try to compile the bootkit with x86, for instance, and it will probably not work. So we first export the toolchain directory and add it to our path. Then we just make the bootkit, and if it's successful, you can see some binwalk output. So you could see the uimage header, you can see the name of the image, you can see the type of compression that's used, you can see the data address, and yeah, some other signatures like the LCMA compressed signature, and also just a version string. So yeah, when you compile the bootkit, you want to plant the bootkit, and this is where it gets interesting. The Linux kernel treats devices with raw flash as memory technology devices. So it's not a normal block device. There are some differences between block devices and memory technology devices. And one of them is, for instance, that the erase blocks that flash devices use are much larger than sectors on block drives. And also the difference between, one of the differences is that when you erase a block, it's basically the same as a write operation. And when you try to remove a block or something from a block drive, it just deallocates it, and then later on you just overwrite it. But with flash devices, when you erase something, you actually write zeros to it, and it will be erased, or Fs. It depends on the implementation. And the memory technology device layer is a layer that is on top of the raw flash, which is a layer of abstraction. And on that abstraction layer, you'll have the normal file system utilities. So what Linux does, it emulates a block device for you to work with memory technology devices. This is when you are on a memory technology device, it will be a proc entry called MTD. And when you cut MTD, you will see, as you can see here, all the devices, and then the device names and the size of the device, the partition, and also the array size of the partition. And as you can see, MTD0 is where we want to be. It's MTD is U-boot partition. And yeah, we just hope that we could just immediately write to the U-boot partition, but unfortunately, that didn't happen. Because the kernel enforces several flags on the MTD flags. And as you can see here, the MTD part section, it contains all the partitions that you could see here. And it specifies a read-only flag on them. But luckily for us, this is enforced by the kernel. So some guy already made a tool called MTD-RW, which is it's a loadable kernel module. And what it does, it overrides the writable flag on all these MTD partitions and basically makes it writable. So here you can see part of the code. So basically what the code does, it iterates through the MTD flags, and it will do it will do I think a binary OR operation when it wants to set the MTD writable flag. And then when you want to unset it, it does a binary AND NOT operation. And then it just resets the flag as what it usually was. So in order to make this work, you need to, again, compile this kernel module with your cross-compile toolchain. And then you can get it on the device. Usually you can get it on the device with SSH or with NCUT. And if the device you're trying to compromise is OpenWRT, you can just install this with the OpenWRT package manager. And as you can see here, you can just do an insmod, and then it will say like, no, in order to make this work, you need to explicitly say that you want a brick. So you need to do insmod, and then I want a brick equals 1. So it's like a disclaimer, and then as you can see, when it's successful, it will clear the writable, it will add the writable flag to all of the partitions. And then when we want to write our backdoor to the U-boot partition, it's successful. So this is very interesting because on normal devices, I mean, you shouldn't be able to write directly to the bootloader, right? I mean, back in the days, I had a motherboard at home, and if I wanted to do something to my SPI flash BIOS, I just had to remove a jumper. But because jumpers are so expensive, yeah, these attacks are now possible. So now that we have the bootkit in place, we want to have a persistence method. So you can do several things, and one of the things that we did is we created an init ROMFS. So we created a malicious kernel, and we can add any file to it. We can add any kernel module to it, and then we serve it with our C2 server. And our C2 server is nothing more than a TFTP script, which expects a ping from the router, and then when the router says like, "Hey, are you alive?" and then we say, "Yeah, we are alive," and then the TFTP command comes in, and then it pulls the kernel from our TFTP boot, and yeah, it boots the kernel. This is a great persistence method because you basically bypass the entire operating system. We just load a custom kernel, and then we mount the actual partition from the device, and we just kick off the init there, and it will just be like a normal device, but it has our malicious kernel. So it does everything that the device used to do, but yeah, we own the kernel, and we can put any file in there, and it's pretty bad. So now I will show, I wanted to show you the demo, but luckily I made a video, and the video will show you the bootkit in action. Before we start, I'm going to explain displays here. Okay, so it's there, I guess, I hope. So the above screen is the serial connection that we have with the router. And as you can see here, when we try to ping our C2 server, the network is unavailable because, the interface is not set up. So the device did a ping, the C2 server did not respond, so it just boots the normal kernel image, which is the basic OpenWRT1 for the GLINet device. And here you can see the kernel is compiled in 2017. It's 3.18.27. And we reboot the device, we start our TFTP server, and the interface is up, so you can see the ping response. And then the device reboots, and it's like, oh wait, I have a ping response. And then it will kick off the TFTP server. It takes a while, of course, to boot this image, but I think it's maybe a couple seconds. So normal users should not, find out that easily. And then when it's ready, you can see a lovely image that means that we backdoored the kernel in this case. This is our fully weaponized cyber toolkit. And it's a newer kernel. It's compiled in February. And we basically compromised the device. So what can you do to prevent these type of attacks? Well, one of the things that they did is, I think, Debian is one distribution that actually started with reproducible builds or doing it on scale, is that, you can create a reproducible U-boot image. So by, for instance, using compile flags like source date epoch, you can create a compiled U-boot image, and you can basically hash the data sections and compare it to other U-boot images and say like, okay, we have a match here, So for instance, what ChipSec does is one of the features ChipSec has is that it can get data from your Mac OS device or your servers, and it just gets the UEFI and it gets all the data sections from the UEFI. So it strips out the variables like a MAC address or a serial number, and it just compares the data sections with data sections that it knows are valid and legit. So when you have a backdoor, for instance, this MacBook we run this tool on, it had a writable flag set, so you could write to the UEFI, and it just immediately detect that. So if we could have tools like this for routers as well, then we could start detecting bootkits like this. Also, secure boot is very important because my x86 device has a secure boot. So if you try to load a malicious kernel or you try to load a malicious kernel module, my device is going to say like, hell no, it's not signed. You cannot do this. And U-boot supports different ways of secure boot. You can have a digest, which you can implement into U-boot. So it basically checks the hash of the U-boot. But you can also do a signature-based one, which is very easy to implement, actually. And then, then you can just verify the U-boot image, and if it doesn't match, you just don't decide to boot it. But one of the problems is that if there's no physical impediments or there's no proper TPN module, then secure boot is as strong as the weakest link in this case. And because we have a root shell on the device, and we can maybe write to the boot partition and just replace the U-boot enabled bootkit bootloader with our bootkit, which just disables the secure boot flag. And also trusted boot is something that they are working on at U-boot. So where you have a TPM module, it basically does the same as on your x86 device. It checks the hashes of your boot stages, and when they add up, you just boot. But you could also do like what the Chromebooks do. They introduced the write protect screw for the SPI flash. So if you want to flash your Chromebook and you want to change the UEFI, you just need to unscrew your the small screw there, and your SPI partition becomes writable. And yeah, this is great. This is basically the jumper on the motherboard. And if Chromebook can do it, I think a lot of other devices and vendors could also start doing this. Bypassing secure boot is also possible by just doing something weird. U-boot disables the verification when it cannot find an RSA key. So as you can see in the code here, is that what the guys did? They found out where the RSA key was in the U-boot section, and they just DD'd it with null bytes. So when U-boot was trying to find the RSA key, it just found null bytes, and it was like, oh, what the hell? I'll just boot this anyway. And another way of bypassing secure boot for U-boot-based devices is by exploiting a Stack Overflow, which the U-boot project is not intending to fix. Is that when you do a TFTP boot, they don't check the bounds of the TFTP boot image. So you can just create a very long device, a very long kernel image, and you could just add some shellcode at the very back. And then together with a JTAG debugger, you could try to bypass secure boot by making a beautiful ROP chain on U-boot. But yeah, it's a hard method, but some guys actually managed to pull this off. Yeah, and secure boot is not perfect. The guys from Riskcure at Black Hat gave a talk. I think it's the Riskcure guys. Yeah, and they were basically glitching their way past U-boot. So yeah, if you have like a compare one to see if your signature is correct, then yeah, you can just glitch your way through it. What's another problem is that yeah, there are also supply chain attacks. This happened quite recently. The CC Cleaner attack. It compromised some networks from Cisco, or the website from Cisco and Linksys, and I think TP-Link or D-Link is in there as well. And if the vendor can't be trusted, then the device cannot be trusted. And what the NSA allegedly did was intercept devices before they were being shipped to customers, and would just backdoor them right there. And then yeah, what are you going to do against that? We need some more resources, and we need more ways to find out how we can protect against these things. There are some verified U-boot resources that you can check out. There are also some trainings that you can do from attacker and defender perspectives. There are some very good documentations on how to protect against this. And there's also a book called Bootkits and Rootkits, which explains some basics on how to protect against these things. And yeah, it's very important to use cryptography in this case, I think, because if you strip all the environment variables and all the variables from a U-boot, and you have a standard U-boot, you just hash it. You make sure that all these images are on the other devices by running a tool such as ChipSec, which basically verifies the entity U-boot partition. Yeah, you can. I think you can. Yeah, get a long way. Yeah, our conclusion is secure boot is important, but of course you need physical impediments and you need a proper implementation. We also need to reduce firmware opacity, because a lot of vendors, they don't want to share the firmware with you, because yeah, they're afraid that you might end up hacking their devices or writing malware. And instead, what a lot of vendors do is that they move away from transparency, and they just try to tamper-proof the device as much as possible, because yeah, they don't want you to mess around with the device. Yeah, we'd also like more people to reverse engineer these firmware images and find out more and more, create better scripts and documentation. And if we can have like proper bootloader parsers for embedded devices, we could maybe end up securing the devices a lot more. And yeah, this is how I end my talk today. So if you have any questions, I don't think we have a lot of time left, or 6 minutes. Okay. Any questions?
Hi, I have several questions. One, your exploit is specific to the architecture. You have tied it to your architecture, the memory layout, the CPU, the so, and you are targeting a very specific architecture. Basically, you find in home wireless routers. Are you aware of this paper, which came out in 2011 in Workshop on Offensive Technologies. It's co-located with Usenix Security 2015. It's 2011. It's called Killing the Myth of Cisco iOS Diversity.
Sorry, I didn't get the paper.
It's called Killing the Myth of Cisco iOS Diversity.
Okay.
It was published in WOOT, which is co-located with Usenix Security 2011.
Okay.
They do a similar stuff on Cisco devices.
Oh yeah,
and the same thing was then repeated on HP printers,
okay,
where they could fire up remotely commands to HP printer to do stuff like print random stuff without your intervention. They do not require, those exploits do not require you to be physically near a router to.
No, we also don't need physical access for this attack. You just need a root
shell. What about that? I mean, what I gathered at some point, you have to play with that jumper to do something.
No, there was if you want to protect devices, you need to add a jumper. But our device, if you have root access to the device, you can basically do anything, and that's because the devices don't have a jumper.
And secondly, you are positioning this for a device.
This is not a question, right? I mean, we can discuss these things later if you want to.
No, another question I have, that you are positioning this with respect to a open WRT enabled device.
Yeah.
What about those which don't have? Because the paper I'm talking about, they don't have, they did not position it against an open WRT enabled device. That's like a Cisco, backbone router.
Yeah, that's great. Yeah.
So, I mean, how many would you find it in the wild?
Sorry?
How many of these would you find in the wild?
That's not we're not going to remotely exploit a lot of these. The point is that you can target any device that doesn't have the right protections, right? I mean, in this case, we just took a case study on one device. And the thing is that you can just target any device. Of course, what these guys did with Cisco, it's amazing. But you can do this on a lot of routers. And the point is not that you can, what you said. I mean, what is your question actually? I don't. My
question is that you are positioning it with respect to a very specific architecture, very specific device. Question is, how many of these would you find in the wild? Why should I worry about this attack? Do I even have this device? How many of these are deployed in the wild?
The attack is not specific to this device. Our proof of concept is specific to this device. But if you would go to your house and you open up your router, you don't see what we see. You don't see a jumper. It probably doesn't have secure boot, and you can do these attacks on that as well. This is just a proof of concept that shows that the architecture of a lot of routers
is working, particularly for OpenWRT, particularly for this kind of architecture.
Yeah, because we use that as a tool chain. But it doesn't mean that you can't do this for other devices.
That's something. It's a little unclear how this would pan out with other architectures.
Let's take this talk offline. We can discuss this one-on-one. Is there anyone with a real question? No, nobody? Right, that's it. Thank you all.